Welcome, everyone. We have a great lecture for you today. We'll continue with Monte Carlo and temporal difference learning in tabular environments, and we'll also discuss Monte Carlo tree search again in a tabular environment. And this brings us to a point where coming Monday, we're going to start function approximation and revisit the methods and algorithms we'll see today and on Monday, but without tables, directly predicting value functions and policies from sensory input. I don't think we have any logistics to take care of, except if you have any question you want to ask. Okay, perfect. So let me just jump straight ahead from where we had left last time. If you remember, we're discussing Monte Carlo learning. Our goal was to compute value functions for policy pi that I would give you. This is the prediction problem without assuming dynamics and reward functions known, but directly using the agent's experience. Do you remember that? Okay, we discussed two methods. The first more in detail, and the second we have just started and will continue today. Okay, Monte Carlo and temporal difference learning. All right? And our goal in both cases is the same. We want to learn V pi of S from episodes of experience of the agent that uses policy pi, right? You deploy the agent and the agent samples actions from that policy pi. And just to remind you, this was the way we would compute estimates of these value functions, capital V. We always use capital letters to denote estimates. We have a present estimate, V, of a particular state, and each time we have an experience, a trajectory, which is a sequence of state action rewards. We have a particular state showing up in our experience. We compute the return, which is the sum of rewards from that state onwards till the end of the trajectory. And this is what is exactly GT, the return. And then we move our estimate a little bit towards the target return. And why we move it a little bit? Because the target is just a sample of the true expected return V pi of S of the trajectory. Okay, so you move a little bit. It's as if you do a running mean of those value estimates. Is that clear? Now, what happens for the states that don't show up in the trajectories of the agent? Well, their values is not updated. Okay, as simple as that. Is that clear? You sample new trajectory, and those states are going to show up in the new trajectories you'll sample. So that was Monte Carlo. So then we saw another way of estimating those value functions, which we call temporal difference learning. And in the case of TD, temporal difference, the target is not the sum of rewards from that state onwards in the end of the episode, but instead it's just the instantaneous reward you get right after that state shows up, plus discounted factor gamma multiplied with the value estimate of the next state that shows up in your trajectory. And that red now quantity, immediate reward plus gamma in the view of the next state. And by the way, rewards and next states are all random variables, right? They change as you sample experience. We just sample them. This is the target. We call this the TD target, okay? And the way your current estimate, VST, deviates from the target, we call it the temporal difference error, right? And each of those tiny updates tries to, minimize that TD error. Is that clear? Is this super clear? What we need to know now is what is our goal? Estimating value functions. We have two different methods, Monte Carlo, TD. And we want to, and last time, if you remember, I had also jumped to this formulation here. This is the recursion that holds for estimating value functions. And we said that Monte Carlo, so you see beautiful expectations here, which hold in the case where you know the dynamics and you know the reward function, right? And now you have you can compute exactly the expectations with the exhaustive summations we saw in the previous lecture when we discussed the value about dynamic programming, all right? And now Monte Carlo and TD approximate those expectations because it's just we don't have now access to those dynamics. We don't have those transition functions and reward functions. And they approximate these expectations using the experience of the agent. And the Monte Carlo methods approximate the second line while the TD methods approximate the last line, okay? And instead of using the true VP, which is, the true value function of the next state, they instead use the, the estimate of VP, okay? Okay, so the expectation essentially is approximated on the last line from the TD, and that expectation in the first and second is approximated by the Monte Carlo methods. Another way we discussed of contrasting dynamic programming with Monte Carlo and TD methods is by looking at their update equations. All of them are trying to update estimates for the value functions, right? Capital V, ST. The way the Bellman backup operation works for dynamic programming is that it looks short and fat, okay? It considers all possible next actions and all possible resulting states because you know the transition probabilities of those and the rewards from rho and R functions. The way the update works for Monte Carlo is by considering one thin thread of experience that goes all the way till the end of the trajectory. And you just have one specific action choice and one specific next state, the one that showed up in your trajectory. Is that clear? All right. And you had said, guys, that the corresponding update for TD is both a single thread as well as short because it considers only one action, the one that shows up in your trajectory, so you don't have expectations over actions. And it uses the next state, the one that shows up in the trajectory, and you use the estimate of the value of the next state as opposed to the estimate of the return. Is that clear? Okay. So what are we going to do next? Well, we'll do exactly the same things we did for Monte Carlo. We'll discuss estimating value functions with TD and then doing control with TD, okay? The same thing we did for MC. So let's see, TD prediction. My goal is policy evaluation. This is also the prediction problem. I give you a policy pi and your goal is to compute the state value function or the state action value function, okay? Q of pi. When we said last lecture that for these lectures, the state action value functions are way more urgent because if I have access to Q pi's, then I can jump to gridification, policy gridification, updating the policy based on those Qs. While if I have access to V, to the state value function, then I cannot update my policy because the gridification, if you want to do gridification with respect to V, you need to have one step look ahead, which you don't have access to if you don't know the dynamics. Okay? Is that clear? Okay. And if you remember the way we used to do that policy gridification in the lecture where we had access to rewards and dynamics, we discussed about estimating value functions for states, V's. But then if you remember, we used the dynamics to go from V to Q. All right? And then we did gridification with respect to Q. Well, this step from V to Q, we cannot do now anymore because we don't have the dynamics function. That's why you need to compute Q in the first place directly from the agent's experience. Is this clear? All right. So let's see. So let's remember how we did this for MC. The value of a particular state is equal to the old value plus alpha, which is a small positive number between 0 and 1, of the return from that state minus the present estimate of that state. And GT is the actual return after time step T, which is the time where this state shows up. The same thing for TD methods is what you see right below. Instead of having the target GT, we have the target being the instantaneous reward plus gamma V of the next state. I mean, we just already discussed about this. We discussed the problem of, going from your office to home. We saw that in the case of Monte Carlo, you need to wait till the end of the trajectory to update your value estimates, while for TD, you don't need to wait, okay? So you're fully incremental. And you can also operate on tasks that are not broken into discrete episodes of experience, okay? So this is the benefit. All right, so let's try to see what are the pros and cons of MC versus TD? One way to understand the trade-off between Monte Carlo methods and TD methods is by looking at the bias and variance of their estimates. So look at this GT quantity. This GT quantity is essentially an unbiased estimator of course, the return of a particular state onwards. It depends on the lot of choices of next state actions and operations of the environment of what is the resulting state and so on and so forth. So it is an unbiased estimator of Epios S, but has very high variance. On the other hand, this target, immediate reward plus gamma V of the next state, it has low variance because it only depends on one action. We have this RT plus 1, but although the immediate reward plus gamma through V pi of the next state is an unbiased estimator of V pi, because you're using your estimate of the value, capital V, you introduce bias there. So if your current estimate is not correct, that it will penetrate on your present value estimate for ST. So one way to think about it is that TD methods essentially have low variance and a high bias, and the opposite is the true for MC methods. We're going to see in future lecture, which is, by the way, a trivial observation, that between MC and TD, there's a continuum. You don't need to consider immediate reward plus gamma V of the next state. You can choose any arbitrary time step that you want, use actual rewards till then, and then use the V of that resulting state. And in fact, in policy gradient maths, we're going to see in exactly 1 week from now, that's exactly what we're going to use. We're going to use for the next 5 steps, immediate rewards plus the V of the 6th step. Okay. So once there is a continuum between TD0, which is 1 reward, TD1, TD2, TD3, TD infinity, which TD infinity is exactly Monte Carlo. You don't use any value estimates of the remaining states, and you only, accumulate rewards. All right. That's it. There is no other confusing thing. It's just, it is what it is. Now, here comes a very beautiful example, though, to see the difference. A-B example, very simple. We have only 2 states, A and B. And what I'm showing you here is 8 episodes of experience, 8 trajectories. The first trajectory is the agent starts from state A, receives reward 0, goes to state B, receives reward 0, and the episode terminates. The next 6 episodes of experience, the agent wakes up at state B, gets a reward of 1, and the episode terminates. And the last episode, wakes up at state B, gets a reward of 0, and the episode terminates. And let's assume that gamma equals to 1. There is no discounting. The question is, from those 8 episodes of experience, what are your estimates? What is our estimates of the value functions of the values of states A and B? This is what it is. So you can use your favorite method, MC and TD or TD, and please raise your hand and say, this is the method I'm using, and these are my estimates. Okay? Because we have 2 methods now to go from, sets of episodes, experience trajectories of the agent to value estimates. Pick your favorite, and then let's discuss your findings. So who would like to start? Yes.
I mean, you could argue that the value of A would be 3/4 within the transition.
Okay, shall we start from the value of B?
Yeah, I mean, if you count up the rewards you get in B, it's 6 times that you use it. 6 of the times you use B, you get +1. 2 other times you don't get anything, so that's what the increase is.
Okay, 3/4, 0.75. Do you guys all agree with the value for B? Okay, and did you use MC or TD to estimate that? Or it doesn't matter?
I don't think it matters in that case. At least not just for B.
Yes, it doesn't matter. Why? Because there is no other states coming afterwards, right? And things differentiate once there is at least one state going afterwards. If there is no state, then both TD and MC do exactly the same thing. They just sum the next reward you just got, which is exactly what you did. Excellent. Yeah, so now you want to start the discussion about the value of A. Yes, go ahead.
I mean, it kind of depends on, as you were kind of pointing out, like it depends on how you model it. But if you think about like A always transition again to B, and with gamma being 1, Like you could argue quite well actually that the value of A is 0.75 as well.
Yeah, great. So now my question for you is your reasoning, which is, look, I see in my experience that A always transitions to B. I know gamma equals 1. I know VB is 0.75. I conclude that V of A is 0.75. This reasoning is in which of the two methods that we discussed, the TD method or the MC method?
It would be in TD because MC just plays out the episode and there's no episode where we get a reward when we start next.
A little bit louder. So your answer is this is the reasoning behind TD, because in MC, and then I didn't hear what you said.
Yeah, in MC, like you pick a starting state and you play out the episode. There is no episode out of the A where you start in A and end up getting a reward. So MC would never capture the reward relationship.
Okay, all right. Well, we have a small confusion here. So now your colleague says, look, I have a trajectory that starts from A, that A shows up, but I don't get any rewards, right? And then we don't know what MC is going to do. Do you want to say something?
Yeah, if you have either TD or MC, since they're both these samples, you have no sample where you start at A, you get any reward. So it never updates any reward other than 0.
Well, I mean, here is our disagreement. So when a state shows up and it says 0, okay, great. So if it doesn't update, then what is the V of A?
It would be 0 in the samples.
Okay, great. And if I had initialized my value estimate for A to be 50 or -1, will I have updated my value for A here?
Yeah.
I would have updated closer to 0, exactly. So the fact that the state shows up by not and doesn't give you any rewards, depending on your initialization, may change your estimate. Now, you guys think of the standard case where we initialize with 0, which is precisely exactly what we do. And very correctly, your two colleagues said, look, if you use MC, right, the value of A is 0. But if you use TD, the value of A is 0.75, okay? And this is precisely the whole point of this exercise, to see how with the same the same set of trajectories, the two methods result on different estimates, okay? And indeed, this is precisely what you said. So the mean square error on the training set is exactly what Monte Carlo gives. But then here is the reasoning that TD does, which is your colleague suggested. He said, we need to think about the transition between the states. That's precisely what is this TD formula, right? So it thinks about which state you started, what reward you got, and where you landed. And then in that case, yes, indeed, the VA would be 0.75. And this is precisely what TD is going to give. Basically, so essentially you try to fit not the value, but rather the Markov model behind your experience, how the states are arranged, what are the transition probabilities, and so on and so forth. Okay, so that's it. Yes, there was a question. Yes.
Can you go back to the experiment, like the AB?
Mm-hmm.
Yeah. So here, we're not updating A after we update B, right? We do one A and then everything after that is just B.
Yeah.
So where is BA going to point that?
Yes. So good question. So now your colleague says the following: what if I start updating my values by looking at the trajectories, right? So I have the first trajectory that says A0, B0, and what will be your value update? 0, right? That's it. And then the other experience shows up, and then what happens? That's it. The VA will never be changed, even if I use the TD method, correct?
Yeah.
Right. But so TD and MC, there is this tiny little alpha, okay? And I want to tell you, somebody can take the same experiences and replay them. Okay, I got some estimates out of those. Let's go back and update. Now the VA is going to be the old VA 0 plus alpha, tiny bit towards the new target, which is that new target will be what? Immediate reward 0 plus gamma, which is equals to 1, the value estimate of B, which is whatever is going to be. So as you replay your experience again and again and again, you will convert to these values that we just said. Another way to think about it is instead of computing running means, you just compute exact means, right? Like you just compute exactly, that's all my experience. I just need to aggregate and that's it. Usually we do running means because experience keeps coming and coming and coming continuously. If I just give you, here's your experience, there's no more compute, then you're just going to average.
That will depend on which I choose to average first. Like if I average B first
You need to keep updating till there's no change, right? Much like what we discussed on dynamic programming, where we iteratively update our values. Is that clear? Till convergence, and then you'll converge with those values. Okay, so basically the order is not important. Okay, but this is a great question. Is that clear, the question and the answer? Yes?
So unless we specifically say that the order is important, we should assume that we're doing like MC or TD until convergence.
So the ordering of experience will never be important, all right? So the alphas, the running means we came up with, is one way to compute the running averages. So for, infinite threads of experience, as you want to keep updating yourself. In general, if I give you a fixed set of experience, you're just going to take, the exact, form of the equations. Or in DP, for example, again, the order didn't matter. You just start, you select the sequence of your states, keep updating them and updating them, until you converge. So we're doing exactly the same thing here. Okay? Yeah. Okay. So let's see. Unified view of whatever we've discussed so far. So we have some backups, and so the width of the backup. So DP has large width and small depth. TD has small width and small depth. Monte Carlo has small width and large depth of the backup. And here, which is both, large depth and large breadth, large width and large depth, is exhaustive search, okay? Where you check absolutely everywhere what is below your tree, and we're going to discuss about this search at the second part of the lecture. Yes?
I had a question about something 2 slides ago.
Mm-hmm.
It's a bit about the maximum likelihood estimate. So I was just wondering, so if you were to build a world model based on the transitions and then do DP, would it be equivalent to DP?
Yes. Exactly. That's precisely what the red sentence says. You want to build a model, and then you want to use it to estimate. Exactly. Okay. So let's yes.
I had a question. Why does it go to value of A go to 0 and TD 0? Because if you think of the update, and value of A is equal to the old value of A plus the immediate reward plus the value of B minus the current value of A, and the current value of B say becomes 0.75, and the immediate reward is 0, then, and the old value of A is 0, so it becomes 0 plus 0.75 minus 0 is 0.75.
Which is how much?
0.75.
Okay.
So value of A will go to 0.75 and TD 0 as well, right? I'm not sure.
But that's exactly what we said. We said the value of A goes to 0.75 for TD 0. And the value of A goes to 0 for Monte Carlo. That's what we said.
Oh, sure.
Okay. Okay. Great. So let's jump to this very exciting topic of using TD methods for computing state action value functions, as well as using them for estimating optimal policies, okay, in our tabular environments. Who would like to come up with our update equation for Qs, capital Qs, because with their estimates, for the case of TD 0? So we know what is for P, we've seen 100 times. The V of the particular state equals the old V plus gamma target, which is immediate reward plus gamma V of the next state minus the present value V of ST. That's it. So how would be the equivalent for Q? Yes, capital Q.
Q pi of state action is equal to the current Q pi of state action. Alpha times the reward.
Yeah.
Plus gamma times the Q of S prime and then pi of S prime.
And then pi over S prime, yes, okay.
Yeah, minus the original Q value.
Yeah, great. So let's see. So your colleague said, first of all, Q needs to have as arguments both the state and an action. And the new value will be equal to the old one. We'll start from some random initialization, we said, right? Probably we usually start from all zeros. Plus a positive value alpha between 0 and 1. the TD target, which is immediate reward plus gamma Q, and he said the next state, comma, the pi, which is the policy of ST plus 1. That's what you said. So you said, let's say, so the policy, here's the thing, the policy may be stochastic, okay? So I think what you meant is the action that was sampled in that particular trajectory, because I will use my trajectory to fit in there the arguments of those next states. Exactly, minus the current estimate. Do you guys all agree with this? And he says you should do that for every transition from a non-terminal state. So you collect experience, and from all states, except from the terminal states, you should do exactly this. Yes?
How are we picking the next action? Should it be more max over all actions?
Yeah, so good question. And let's make sure we don't get confused here. I give you some experience. You give me a policy. I take my agent, I deploy it on the environment and allow him to sample actions from your policy. And that's how I'm going to get the actions. The actions are those the precise things that are going to show up in my trajectories. Here, the actions are random variables, but you're going to be feeding in the actions that you show in the actual trajectories. Okay? All right. But we'll go back to your comment. He said, why don't we take maximum across all actions? That's what your colleague just said. So we'll see this is also another way to form updates, but we'll see this in a second. To me, the most straightforward way to adapt the value update for state action is precisely what your colleague just said. What do you think? All right. So now we will go to the control problem. To the control problem. And would somebody would like us to remind us how we did control with Monte Carlo methods? Control meanings find an optimal policy. Like in high level, what did we do? Yes?
It was like considered all the rewards that were just coming all the way to the end of the
Right. So by control, guys, I mean control. I mean, we start with the policy and the value function, and we keep updating that policy till we find an optimal policy. That's what we define the control problem to be. All right. Essentially, policy iteration, iteration between policy evaluation and policy gridification, and then policy evaluation and policy gridification. We did exactly that when we discussed among Monte Carlo methods in the previous lecture. We call it MC control. Okay. Do you guys remember roughly how we did it? We said, okay, I'm going to try to find an optimal policy, but unfortunately, I don't have dynamics and I don't have rewards. So what I'm going to do? What do I need, first of all, to do policy gridification? I need the Q, so I'll be estimating the Q. That's the first thing we said. Now, the second thing we said is that if we want to estimate Qs for actions that my deterministic policy doesn't take, I better have an exploratory policy, a policy that explores. That's what we said. Otherwise, we'll never be able to improve and find advantage. That's another thing we said. And then we put down an epsilon greedy policy, if you remember. We also had some other options of exploratory starts, which was a little bit crazy how we were sampling the initial state and action from everywhere, independent of the policy, right? To ensure that every state and action is sampled in our experience. In any case, we all concluded in some baseline method to do MC control, which was, let's put down an epsilon greedy policy. Let's keep sampling from that policy to get experience. Let's estimate Q. And let's update the policy by taking the epsilon max over that Q, which is precisely the gridification step, right? Essentially, this is going to change the action choices per state if you take epsilon max with respect to epsilon Q. And once the policy has been updated, what did we do? We went back to the environment, recollected experience, and recomputed Q, and again gridify and recollect experience and compute Q and gridify, etc. Do you remember that? So we should do exactly the same thing now. It's just that instead of using Monte Carlo methods to compute Qs, we're going to use TD methods. The update that your colleague just suggested, that's what we're going to be using, okay? So instead of GTs, returns, we're going to be using this R plus here, R plus gamma Q. So here's the pseudocode. The pseudocode is initialize some Q randomly, arbitrarily, all right? And, when I give you a Q, naturally the policy falls off by taking epsilon greedy with respect to that Q. And then it says, choose now, take your agent and deploy it in the environment and make sure the agent samples actions from that epsilon greedy policy that is derived from the Q state action value function. Does anybody want to remind us how we'll go from Q to action selection? Yes?
We'll play the maximum action given this. We'll play the maximum action that maximizes QSA given the state 1 minus epsilon of the time. And epsilon of the time will sample an action, a valid action from the state.
Yeah, so a valid action, because we don't know valid, no valid, we just sample any action. And each of those actions has probability sample epsilon divided by the number of actions. So that might be also the argmax. So your colleague said we're going to be playing argmax 1 minus epsilon % of the time. And with epsilon probability, we're just going to sample an action uniformly at random. Great. That's the policy that comes out of the Q. And this is what this says as well. And then, so you take an action, you see immediate reward in the next state, and go straight away and update your Q estimates. You see, so here the experience comes and you update your Q immediately. Okay, that's fine. That's okay. I mean, you can also just explore, collect a bunch of experiences, and then go and update your Qs. That's what we'll be doing in a couple of lectures from now. That is fine. And this method is called SARSA. Why it's called SARSA? Because it's like SARSA, because of the update form. Okay, that's how it's called. All right, great. So very simple, very intuitive. Here is an environment. We have an initial state and a goal state, and there is a wind that blows and has some. You get a 0 reward or reward -1 till you reach the goal state. So the goal of the agent is to reach the goal state G as fast as it can. There is a wind blowing with some force that is 0 for the first 3 columns, and then 1 for the next 3, and 2 very strong wind, and then low wind, and so on. And the point of that exercise is that a policy can totally get looped into infinite episodes where neither, it doesn't terminate, and MC methods essentially cannot handle this because they need episodes to terminate. Now you may say yourself, I will myself define a termination of the episode and update my estimates and restart my agent. That's totally possible. Well, TD methods naturally handle this because as experience keep coming, you don't need to wait any termination. That's what we just saw in the pseudocode. Every single experience, you can update your DD function. If you see you're doing well, you just straight away update your action choices. The derived epsilon greedy policy will be different. Okay? So this is the example that shows up in your book. Okay, that's it. So now we're going to see a second TD control method that is related to what your colleague suggested. We're going to call this method off policy, not on policy. Let me remind you what we call on and off policy. On policy is when the policy for whom we compute the Q values is identical to the policy we sample experience from. And indeed, in the previous pseudocode, that was the case. That was the epsilon greedy policy. Now here, we're going to have 2 separate policies. The policy that will collect behavior should always be exploratory, so that's going to be still epsilon greedy. But the policy for which we're going to be computing Q values will be, let's say that it will not be epsilon, it will be deterministic, or at least it will break ties arbitrary or random across the argmaxes of the actions. So these are going to be these 2, we're going to consider these 2 policies, okay? And this is very much related to what your colleague just said. And why this is the case? Well, let's check out the pseudocode. The beginning is still the same. We initialize capital Q randomly. And then we go and select actions. And indeed, the actions are selected from the epsilon greedy policy that is derived by that Q function. But then the update is not SARS update, is essentially look at the target, immediate reward plus gamma max across all actions of the Q of the resulting state. All right. If you remember there before, we had the action that was showed up in your experience, but now we have an argmax. Okay. So we're computing the Qs of the policy that always would consider the argmax of actions for the next state. And this is called the Q learning update rule. All right. And we'll see the deep Q learning equivalent on Monday or Wednesday next week. And just to remind you, here is the SARS update rule. Now there is a very awesome example now we're going to visit that will show you exactly the differences between on-policy control with SARSA and off-policy control with Q-learning. All right. So here it comes. Do you have any questions so far? Yes?
In the slide about the windy gridwork, where the agent took this sort of apart.
Yeah.
I'm curious, why did it not go down at the point where it took it upwards, and it would have taken much less time to get to G?
Well, because there is a very strong wind force there at the environment, the transition dynamics on the environment around those columns where you see the bold arrow is that no matter what you do, the environment pushes you up by two states. Does this make sense? There is a wind blowing from the bottom of the chart to the top of the chart.
Is the wind kind of infinitely strong?
No, it has two. I mean, I don't remember the exact wind dynamics. I think it pushes you up by two values. You are, let's say, at the bottom row, and it pushes you 3 rows up. While before it was pushing you 1 row up, depending on 0, 1, 2. This 0, 1, 2 essentially denotes the wind strength. Yeah.
I guess I'm wondering, I mean, assuming regular experience with regular physics, if I go...
I mean, sure. I mean, without the wind, you better, there is also a shortest path solution here. Just go straight.
I mean, assuming so at the end, the agent did take a downward path.
Uh-huh.
So it's able to go vertically downwards, right? So if I go vertically downwards enough, then the wind pushing me up should take me to G directly.
Yeah, let me double check about this solution with a book, and then we'll discuss it in the office hours on Monday. Okay? Because I don't remember the exact wind dynamics, so I cannot say something useful. Yes.
It's both SARSA and on policy trying to learn the optimal policy and the Q for the optimal policy at the same time.
Very good question. So your colleague says, is SARSA and deep Q learning control algorithms try to find the optimal policy? This is what you're saying. Does anybody want to reply now before we see our example? Yes.
SARSA learns the optimal like epsilon greedy policy, but Q learning would learn the actual optimal policy that is deterministic.
Yeah, because the other one, no matter what it is, you will always, with epsilon probability, break, sampling actions uniformly at random, which are going to be suboptimal actions. Okay. Yeah. So let's consider now this specific environment. It's called the cliff environment. There is a state, initial state capital S, and a goal state capital G, where you really want to go. You are going to get a reward of -1 for every time step that you do not reach the goal state, and you'll get a reward of -100 if you fall on the cliff. Okay? And the goal now is you have an agent. Of course, we have discrete actions. You can go up, left, bottom, right, and so on. And you want to find the optimal policy of operating on that environment. Okay, so we can easily see that the fastest way to go from the initial state to the goal is that red path. Do you all agree? That could have been the optimal policy. And indeed, this is the policy that deep Q learning rule finds. Okay, the off-policy TD control. Now, the on-policy TD control, which we also call SARSA, finds the blue path instead. Why this is the case, you think? Yes.
So the blue path, like in that epsilon blue row, is gonna not fall in the cliff as much. And the SARSA update cares about the whatever actions actually happen, so it takes into account if we choose a random action, we fall off the cliff.
Mm-hmm.
Whereas the red path, it's finding the optimal, the actual optimal values. So it's not concerned with the fact that if you with probability of some reaches and you fall off the cliff, because these are the optimal policy steps.
Yeah. So your colleague said the following. Despite the fact that in both cases the epsilon greedy policy collects the experience, the Q values that we'll be estimating will be completely different in the two control methods. In the deep Q learning method, those Q values will reflect the policy that takes the argmax across all Qs for every state, all right? And indeed, the highest Q values will be of those states that are along the red path. Of course, the ones that are closer to the goal have higher Q, and then the other will have lower Qs as you go close to the beginning, right? While in epsilon greedy Q estimation, those the Q values of the state near the cliff are going to have low values. Why? Because many actions will send you off the cliff, and this is taking into account in the SARS algorithm. If you remember, the Q S comma alpha of the target, of the TT target, is instantaneous reward minus 100, okay, plus gamma resulting S comma alpha. And each time you jump on the cliff, this is going to be affecting the Q values you're be estimating on your SARS algorithm. Is this clear? Okay, so if this is clear, I have another question for you. The second question is, in this bottom diagram, what you see is here's the training experience of the agent with respect to the number of episodes. And on the y-axis is the sum of the rewards during the episode, like how well is doing at training time. What does this mean? This means the experience you're collecting. What are their rewards? Are they high or low? That's what this is asking. Okay, those experiences that you're collecting with the epsilon greedy policy, how well they're doing. Okay, and what I see is that SARSA is doing better. Okay, the trajectories of SARSA have what? Higher rewards, which means they fall less on the cliff. Okay, why this is the case? Yeah, yes?
Because the policy of Q learning is not for the epsilon greedy policy, so it learns a really unsafe policy, which can fall off the cliff, whereas the SARSA policy is conservative. And during training, says that the optimal policy has to be conservative because it's an epsilon greedy policy. If you change it later and remove the epsilon greedy thing, then the Q learning should perform better.
Of course. So now your colleague said, you know what? If my Q learning algorithm was collecting experience with the argmax, which is the optimal policy, or at least not the epsilon greedy, but like the greedy policy, let's call it greedy. And let's say between us, we understand that, for the argmax actions, you can put arbitrary probability between them. But let's talk about the greedy policy. He says the greedy policy trajectories will look much better, right? But these are not the greedy policy trajectories. These are epsilon greedy. Because if you go back to, how Q learning operates, let's see how we collect experience. Here, we collect experience. It says, example, given epsilon greedy. We use the epsilon greedy policy when we collect experience. And yes, and the epsilon greedy actions with respect to Q will send you towards the cliff more often because the Qs are not conservative, okay? Because they are computed for the optimal policy as opposed to the epsilon greedy policy. Is this clear? Yes? Yeah. So I think now your colleague said, do we really need the epsilon greedy policy to collect trajectories when we have the Q learning rule, or we can put an arbitrary policy? Is this what you're saying? Excellent question. We'll have a whole lecture on that. It's called it off policy reinforcement learning or offline RL. And it has very interesting answers. And the answer is no, you cannot use ready algorithms, what we describe right now, to just apply them on arbitrary experience. Okay? And we'll explain there why, and we'll propose other methods. Okay? But great question. Yes. Other questions? Yes?
Can there be some methods where we reduce that exploration and still achieve something like Q learning? Eventually the policy won't fall off the cliff.
Yeah, so here, with Q learning, eventually the policy doesn't fall off the cliff. You fall off the cliff during training, you learn the optimal policy, and when you deploy it at test time, you don't fall off the cliff. You follow the red curve. Okay? Do you see? Yeah. But the training time is not a safe exploration. You'll be falling off the cliff a long time, or many times. Other questions? Yes?
Imagine if the cliff was incredibly long, you might have a problem with regular Q learning where you never reach your rewards, you never get that propagation of rewards backwards. Is there any case where SARSA might outperform Q-learning in terms of time it take, like overall training performance?
Yeah. I think what you're saying is the following. What happens when the rewards is really far away in the future? Will one method be impacted more than the other methods? I'm not sure why one will be impacted more than the other. I think this is detrimental for both reinforcement learning methods. Do you see? I don't see why one will be worse than the other.
Oh wait, never mind. I think I figured out my mislogic.
Okay, and by the way, this is detrimental for all reinforcement learning methods. So we'll see why this is all these things we're discussing. In the general case, when rewards are super far away, they're a little bit hopeless. But you know what? Many times the exploration can be really nearby. Your goal is there. You know what you expect to do now in the next, few milliseconds, and you just need to optimize. And all these methods we're discussing are going to be very, very valid algorithms for you to use and to actually achieve your short-term goals. All right, and we'll take care of long-term goal setting with some other methodology and so on. Okay. All right. Now, one more thing we need to discuss with deep Q learning, which is called the maximization bias. Let's consider this very simple environment where we have two states, A and B. You always start from state A, and you can go either to the right and get a 0 reward and then go to the terminal node, or go to the left and you will land in a state B. And out of state B, you're going to have many action choices whose mean rewards are sampled from a Gaussian with mean value minus 0.1 and some variance of 1. Okay, much like in the bandits methods, you have multiple actions and you have the mean rewards. Now, unfortunately, the mean reward of each action from state B to the right is unknown to you. I mean, I have it in the slide because we are starting a discussion, but the agent has no clue about that mean 0.1. He's trying to estimate that from experience, all right? And he's trying to compute the optimal policy. What do you guys think is the optimal policy if you wake up at state A? Which one maximizes the rewards? All actions have mean reward minus 0.1. All right, it's just the rewards are not deterministic. There are some random variables, and you may do exactly the same action, and each time you do, you're going to have a different reward. And I'm saying all those rewards are random variables that are sampled from this Gaussian distribution that has mean minus 0.1 and variance 1. So what is the optimal policy here, guys? Yes?
Right.
Go to the right. Is there anybody who disagrees with this? No, because on average, if you go to the right, you'll get a reward of 0, while on average, if you go to the left, you're going to get a reward of what? Minus 0.1. Now, here is the problem. Let's do off-policy TD control, which is the second control method we saw in the TD methods. Okay, so we will be using some inside the TD target there is instantaneous reward plus gamma Q of the state, and then argmax across all actions of our estimates, capital Q. That's the problem. So we'll be taking an argmax over all actions that we've seen from state B and to the left, okay, at some point. And unfortunately, because you're sampling, there's going to be some action for whom the estimate will be positive. Okay, so you may have gone multiple times from the B to the left, and there's going to be some actions for which that estimate will be positive simply because you're sampling. Okay, so most of your actions from B onwards will be negative because they're sampled from minus 0.1, but there's going to be some actions for which it's going to be positive. And the problem is that because you're taking this argmax, despite the fact that if you had the golden Q, the true Q star of the state of B, argmax across all actions of that Q, this is going to be, let's say, minus 0.1. Unfortunately, because you're using the estimate capital Q, this can be misleading, can be above 0. Do you see the problem? And essentially, that's what you see in the two curves. That if you do Q learning, it takes you very long time to realize that you need to go from the other side, that you just need to go to the right. Okay? Okay? Yes.
I was wondering, I feel like this problem we've already solved in the battery case by using upper confidence bounds and things like that. Can't we simply use like a UCB method to sample actions instead of argmaxing or epsilon greedy or anything like that?
Yeah, so no, we're not going to use this there. If you remember, the UCB was per action. We were estimating per action those values. Okay, UCBs are going to come back with us in about 10 minutes when we talk about planning. And again, there for every state in action, we'll compute a UCB. For Q-learning, we don't use UCB, and the reason is that soon we're going to go to continuous state spaces. And there is going to be a little bit not obvious how to estimate your uncertainties. All right, okay. But there is a very simple trick. This, by the way, is this argmax across k random variables is a standard thing in statistics. And in 2010, the solution was proposed, or maybe even earlier than that. And the solution is extremely simple. You have your experience. And instead of computing one Q function, compute two of them, and take argmax with respect to one, and estimate the argmax with respect to the other. And those different Q functions, you should use the experience should be some part of the experience should be used to compute the first, and some on the other. Okay, so if the argmax says, oh, the best action is action 3, I have positive reward there, then the other Q function will evaluate that action 3 and will tell you, no, it's not. It's minus 0.03, for example. Okay, so you break in this way your maximization bias. All right, but of course this ensures that the two Q functions use different experience to compute. So this is called double Q learning. We're going to be computing two Q functions, Q1, Q2. We will never be updating both on the same time step. That's exactly what we said. We want them to be decorrelated. So you pick one at random to update, and then essentially the update rule is the following. You take argmax with respect to Q1, but you evaluate with respect to the other, with respect to Q2. And when you act in the environment, right, you need to do epsilon greedy with respect to Q, you may as well average them. So you do epsilon greedy with respect to Q1 to the sum of Q1 and Q2. Is that clear? So this will fight the maximization bias. So here is how the pseudocode will look like, exactly like TD off-policy TD control, exactly like Q learning, but now we have two Q functions. You initialize them randomly, and then you repeat. You sample an action from the epsilon greedy policy that is derived from the average of Q1 and Q2, and then with 0.5 probability per transition, you update either Q1 or Q2, and the update rule is exactly what we said, is the Q2 of evaluating the argmax with respect to Q1 or the other way around. And that's it. And this is called tabular Q learning. And when we're going to use deep function approximators, we'll call this double deep Q learning. As simple as that. Okay. All right. So there is only one more update rule that we want to discuss, which is called expected SARSA. And it's exactly like SARSA, but there is an extra summation over all possible actions. In the SARSA rule that your colleagues suggested, we were only using the action that we sampled and that shows up in our trajectory. But we don't need to do that because we know our policy. We may not know the environment, we don't know the dynamics and rewards, but we know our policy, we know exactly what probability we assign every action. So we may as well use that to evaluate the goodness of the next state, ST plus 1, under our policy. And I mean, we can, this expected SARSA may show up on some of the next lectures. Overall, it costs more. Why it costs more? Because you have this big summation. All right? You have this big summation to take care of, while in the previous case, there's no summation. You just use the action that you sampled. Okay. And is expected SARSA on policy or off policy? Let's say we have an exploratory policy and we collect experience, then it is on policy, okay? So with the policy with which we collect the experience and we evaluate is exactly the same. Okay, so that's all I had to say for MC versus TD. And now I would like to jump to Monte Carlo tree search. Okay. So I really want you to pay attention because in the next lecture, which is Monday, we'll talk about deep Q learning. And there is a fantastic paper that actually you can read in the weekend that will be an assigned reading for that class, which is learning to play Atari games from offline Monte Carlo tree search. And of course, there's going to be also the standard deep Q learning paper, learning to play Atari games better than humans and so on with the deep Q learning. And there we'll contrast planning versus learning from experience, all right? And it's an extremely important read for you to, understand what planning can do and what the reinforcement learning can do, and when we choose one and when we choose the other, all right? So whatever we're going to discuss today is very valid for Monday, as well as in future Monte Carlo tree search lectures, where we'll discuss about AlphaGo and AlphaZero methods and all these nice algorithms that came out from DeepMind for playing Go and playing other games, by the way, and they're right now the de facto for playing, this type of strategic games with computers. Okay, so what is planning? Well, planning, the way we defined it, at least in our first lecture, was that I give you a model of the environment, and you need to use your planning method to come up with a policy. That's what we said. And what we said as learning is that, I have some experience with the world, and I learn from that. So we didn't call learning, the use of a given model to compute policy functions, but I would say that this is not an important definition. By the way, this is a philosophical discussion. For example, when I sit on my office and I don't interact with the world, but I all the time think and evaluate alternatives with my brain, I with mental practice, I may come up with better policies and choices without any interaction. Is this called learning or planning? According to that slide, it's going to be called planning. According to other researchers, it's going to be learning, okay? You can use your mental model of other world to make better choices simply by thinking deeper. It's just humans usually don't think deeper. It's just very intuitive, very, how they feel about the, particular situation and so on. Okay. Yeah. All right. So what is online planning? Online planning is a very old, and well-known, process, which says the following thing. You want to solve a very difficult problem. For example, you want to beat the world champion in chess. And what you're going to do is you're going to give up on trying to solve the whole MDP. And you're going to say, I'm in this particular state right now of the world. I want to use all my resources to help me figure out how to act right now from this particular state. Okay, that's all it says. And it says that, you'll use the model of the world. So the model in this now part of the lecture is known, dynamics and rewards and so on. And you'll, query it forward. And it's called unrolling. When you use the model forward, it's called unrolling to help you choose the right actions, right? To learn the right policy. That's what it means, online planning. Online means that on the fly, while you're playing the game, you're in a particular state, you use the knowledge of the model of the environment, which is how chess is played, to unroll it forward and evaluate all possible alternatives allowed from your GPU and CPU resources to figure out what is the action you're going to select in a particular state. Is that clear? And this part of the lecture is exactly about this. Now, the crazy thing is that you're about to play with Kasparov, and in this part of the lecture, you didn't do any pre-training at home. You just show up and do online planning. Do you see? You have not gained prior knowledge in terms of, from this state, I think this is the best action. Let me remember that when I go to play. You didn't do anything. You just showed up there and start to do planning because you're very confident on your resources. But in a later lecture, we'll see how we combine prior experience with online planning. Okay? Is that clear? This is exactly the AlphaGo method. And in a further lecture, we'll see how we're going to use planning to train policies better at training time. But this is very, very legit also setup, all right, which we're going to see today. So why we need to do online planning, okay? Why we need to do online planning? Why don't we just learn the value function offline, and we don't need to waste time online? We don't need to, we're going to go show up in the game. We say, oh, this state, okay, great. I know the value. Here is this one. I have pre-computed my queues, okay? And I just do argmax for every state that shows up. I'll do argmax over all possible actions, and I suggest the action. And in this case, during playing with the, opponent, I don't need to stress because I don't need to do all crazy look-aheads and so on. And in fact, all our lectures so far was exactly about this: compute value functions, compute queues, so that you can derive the optimal policy and so on. So why don't we just do that, right? I'll give you chess. Even you know rewards and dynamics, you can use DP. You can, if you feel hopeless about the large state space, you can use the Monte Carlo and TD methods we discussed and so on. Compute the value function and go ahead and play it. So why we need to plan? Does anybody want to say something? Yes? I cannot hear. There are too many states, and unfortunately, the approximation is going to kill us. We're not going to come up with awesome value functions for all the states. There are just too many, okay? And you know what? Most of them, they're not going to even show up during our training time. It is totally possible that while playing with an opponent, I'm going to see states that have never showed up. And for our tabular methods, this, by the way, is, there's nothing you can do. For function approximation, we're going to see next week. You say, don't worry, my features are great. They generalize this state I've never seen, but it looks like that other state, so I better do this that I did in this other state. So this reasoning is behind the representation learning methods we're going to see next week, okay? But we don't know that now. Today, we're still in tabular methods. Every state is a row on the table. So that's exactly what your colleague said. There are too many states. It's very hard to compute a good value function for each one of them. And most of them you'll never visit training time, by the way, and your tabular methods just cannot do it, right? It's just impossible. So people before having representation learning, they had no other way. They didn't even know how, I can train for some states, and what I train, my value function will generalize to the other states. All right, because we potentially didn't have this, setup. So the idea of online planning is, let me not try to solve the whole problem. Let me just condition on the current state that I'm in and try to figure out the best action possible. And I'll focus all my resources in this sub-MDP, which is rooted, as you see, the root of that sub-MDP is the state where I am right now. So let's see how we're going to do it. We're going to build a full search tree rooted at the state I'm in. And you know what? That search tree must be much larger than if I consider all possible initial states and all possible, board configurations. And I will select the next move to execute, and then I'll execute it, and I will go ahead and do the same thing. And the problem is, again, unfortunately, still, there are just too many. It's just too many things to evaluate. So exhaustive search is no good. This sub-MDP is still too large. Too many actions possible. Large branching factor. We saw this in TD Gammon. Due to the dice, the branching factor is even worse. Too many steps, large tree, depth, and so on. So I cannot exhaustively search the full tree. I cannot. And here's an example. And so here's an example of the game of Hex, which doesn't sound very, fun, but this is what it is. Now, the truth is, though, that Deep Blue was, essentially used that search. It used that search. For a particular state, it was checking forward, but it was trying to do this kind of intelligently, which means what? So instead of exhaustively checking all possible next stage and actions, you will do some more pruning, intelligent pruning of that search in the following way. Two things you can prune. You can prune what actions to check by having a policy over them and says, okay, this action has very low. My probability for that action is really bad. Forget about that branch. Let's just focus on those set of actions in this particular state, as well as depth pruning. You land in a state, you're like, okay, this is horrible. For sure, I'm going to lose from now on. Let's not just explore alternatives beyond that particular leaf node. So you can essentially prune the breadth of the search and the depth of the search. And the person that prunes the best wins. That's what it is. So a lot of our lectures is about how do you do this search intelligently. So Deep Blue also used an intelligent search. It was computing value functions exactly this. The first paragraph is exactly about that. How do you compute values for different states so that you can prune branches? Okay, and the second is how do you compute policies so that you can prune also branches but actions. So the value function, there are two ways you can do it. Either you can engineer them, so you hire chess masters to tell you these are good features, let's compute, use those features to compute some value from this set of games and so on. Or you can learn them from self-play, which is precisely what T.D. Gammon did, if you remember, okay? And yeah, so human engineering is difficult, it's tiring, and it's not easy to transfer across domains. While if you manage to do it in the, self-play trial and error way, you'll solve today Go, and, coming week, you're going to solve chess and, shogi and all these other games, you see? So the method generalizes if human is not involved to give you insights. And these insights are rather discovered by the agent herself playing against itself. Right? I mean, I'm just saying obvious things here. All right. Yet, yeah, this is what Deep Blue did. So today, we'll do the following thing. We'll start with Monte Carlo search. So what is Monte Carlo? Whenever you hear Monte Carlo, it's about sampling, right? Because there is this famous casinos in Monte Carlo. So we're showing up in a particular state S. And then what I'm going to do is I'm going to sample from my policy randomly, and I'll collect threads of experience from the current state till the end, where either I lose the game or I win the game. And by the way, right now, I'm not playing. The opponent is waiting for me, the time is clicking, and I'm just sitting on that same state, and I'm sampling mental threads of experience. Is that clear? All right, so from these mental threads of experience, let's say I managed to sample 100. I see how many times for each action that is possible from my current root node state S, a particular action, let's say. This is, for example, putting the black stone there. How many times did I win? If I do that, how many times did I lose? And then I compute what? An estimate of what?
Probability of the
Of the expected return from that state and that action, which is precisely the Q, the capital Q, right? So I estimate state action values from my trajectories. Exactly the same thing what we did earlier in the lecture, okay? It's just what is the difference between this part and what we did earlier? All states are rooted in the particular state that I care about. Okay, it's not just, okay, sample a state and start moving around and then sample another state. No, all trajectories start from the particular state I care about. Is that clear? Yes?
But could I remember if I come again in the particular state that I've encountered it earlier in online lab? So could I reuse my knowledge from the states that I've found?
Very good question. So your calling is saying, first of all, right now, just to be clear, these trajectories, so let's go back to your question in a second. These trajectories, what policy I'm going to use to sample them? Given that I told you you came unprepared to play the game, we'll use the random policy. We'll use the random policy. And your colleague is saying, okay, even if I start random, is there a way that I can be improving over time? Is this what you're asking? That's exactly right. We'll get this to a second. But that's precisely, so here is in pseudocode what we just said. Okay, you're in a particular state, all right? And then what we would do, essentially we sample experiences, how many trajectories equals to the number of samples, and everyone needs to terminate. So that's why it says while not terminal next state, just keep sampling. And here it says also random legal move. And why we can do legal? Because we have the model of the world. So I very much know that, putting the stone there will take me out of the board configuration is impossible. So I know what are the legal actions on every state. In fact, I know everything. I know the model, as we said. And then I just compute how many times I won versus lost versus how many trajectories I sampled. And that's how I can compute a value for a particular state. And the value for that particular state is exactly, remembering which action I took is also give me an estimate of the state action value for that state and action. So in the Monte Carlo search, it's super trivial. I have a model of the environment. I just sample experience with a given particular state and action. And then, I average the returns. And then this gives me an estimate of the true state action value of a particular policy. This for now is the random policy of that state and action. and then I'm ready to play, and I'll just select the argmax. And I think that we all think that this is not going to give a very winning strategy, because these trajectories are not very intelligently collected. They are collected with you playing randomly. The moving, legally, like the horse is going to go the right place. We're not going to violate the rules of the game, but there's going to be pretty random play. So that's it, though. So you start with the environment, and you compute, you evaluate every action for the root state where you're in, and you take the argmax and you play, and now it's the opponent's turn to play, correct? So that's all. This is the simplest possible Monte Carlo search. It's online planning. It uses the model to compute some actions. And the question is, can we do better, right? Can we do better than that? Who would like to tell us how to do better? Your colleague suggested something. So what did you suggest? You suggested, okay, out of the trajectories that we compute and the Q values we get from those actions, what if I update my policy? So next time that I will be sampling, trajectories, I can use the Q estimates that I have, given that the particular action was much worse. What if I, don't sample it anymore when I collect experience, correct? Correct? Okay, so this is exactly what Monte Carlo tree search is. Can we be improving our action selection the more mental simulations we do? That's all it says. And here's how specifically we're going to do it. Because the details are important. Now you just said, oh, if I go back to the same state, maybe I can reuse. I agree, but why not for the same state? What about the next state? For the next state, you also have some experience. These are the sub-trajectories that are, starting from that next state. Is that clear? So you may reuse experience from there as well. Okay. So what Monte Carlo tree search does is it maintains one tree, and for that tree, it bookkeeps Qs for the state and actions, Q estimates. So you have two policies. One is the in policy, the internal to the tree, and the external to a tree. So the external outside of the tree, we're going to still be playing randomly, but internal to the tree, we're going to be playing intelligently. We're going to be using capital Q estimates and upper bounds. So we're going to use the UCB to sample actions. So we're also be balancing exploration, exploitation. So we're going to do something very intelligent inside the tree and something completely random outside of the tree. But over time, this internal tree will be expanding. So overall, our policy will be improving and improving and improving, okay? So that's all this says. So we're not going to do epsilon greedy. We're going to use UCB, exactly what your colleague suggested earlier. Just to remind you, in UCB for every action, we had the capital Q estimate of its value, as well as a upper confidence bound, which is what comes after the small c. And T is how many times I have visited the parent node. And NTA is how many times I visited this particular action. And so now the probability of choosing an action decreases with the number of visitors, of course. So, and it decreases with the node's value, QT of A. Okay? So I want to be sampling actions that both have high estimate, capital Q, and have low NT of A. I haven't tried them a lot. Correct? That's all it says. So that's how our policy is going to be structured within what we call the tree. And now I'm going to show you a nice picture of that tree. So we'll come back to this, yes. So here is what it is. So we'll do the following thing. So for the nodes that were seen before, we're going to be selecting actions using the UCB criterion. Each time that I collect one experience, at each trajectory that I collect, I will be adding an extra node to the tree in a way I'm going to just show you. For that node that I add, I always need to try every action at least once. And before I try every action at least once, I'm not going to play with UCB. UCB I use once I have tried all actions in a particular state at least once. Okay? Because, by the way, in that case, the NTA is 0 and it's on the denominator and things blow up. Okay? So always I'll need to try every action at least once. Then Beyond the tree, I will just sampling from the random policy till I go to the end of the game where either I win or lose. And so no UCB outside of the tree. And once I won or lost, in my mental simulation, what do? I go back to all the states that I visited inside the tree and update their values. Exactly what we did with policy evaluation with Monte Carlo or TD, right? I will look at the trajectory, see which states and actions I visited, and I go and update their Q estimates. That's all. And here, instead of just updating the Q estimates, I also need to update the UCBs, right? Because the NT of alpha has changed. So I need to bookkeep which actions have been visited. Okay. So how do I sample with the UCB? Well, that's all it is. It says you're in a particular state, all right? And it says for the child, you take the value. Okay, yes, that's it. This is exactly what the UCB criterion shows. And so MCT sample. So this is the whole pseudocode. You're in a particular state, and you need to make sure, first of all, that all actions have been tried out. If all actions have been tried out, which means all children of that state have been expanded, then you are okay to select based on the UCB criterion your next node. All right. Otherwise, you need to expand an unexpanded child. That's all this says. Okay. And once you expand the unexpanded child, this is always happens on the frontier. And from then onwards, you play randomly. And I'm going to show you now a nice picture of that. So random play out is what? You just if the state is not terminal, just keep playing and sampling actions from the random policy. That's all this means. And update value means what? You go back and update for the states that you have visited, the visitation count, as well as their value. And here is how it looks like. The root node, so this whole job is done to be able to play at one state. Okay, so the opponent is still waiting for us, and we're building our trees. So we have a root node, a special node, which is what it is now in the actual environment. And then we start collecting trajectories. And at the beginning, the shaded region is going to be very small, only the root node. And that shaded region keeps expanding. With every trajectory I collect, I expand that search by that shaded region with one node, one state. Is that clear? Okay. So what do we do? So here in a particular state, and if all children are expanded, and indeed, for all the states in the shaded region, all children have been expanded, and then I select one action, this is the dark black, the dot, based on the UCB criterion. Yeah. And then I keep doing the same thing. This is called MCTS sample. This is sample using the inside the tree. So here what it is. So up, and now we landed in a new state for which not all children have been expanded. So now what I need to do is I'm going to do a random play out till either I win or lose the game. So here is the end. So let's say I won. And then I go and I update the values of all the states and actions that I visited. That's how it works. And you will get the opportunity to implement this in one of your homeworks. Okay. All right. So let's see, because I need to let you go. So here is the picture. This is the last slide. I select, this is within the tree. I expand once I reach the tree frontier. I do a simulation using a random policy outside of the tree, and I go and update the values of all the states that I have visited. Okay, those that you didn't touch during that trajectory are not updated. So that's it. That's all about Monte Carlo tree search. You need to read the corresponding part of your book about this procedure, and hope to see you, of course, on Friday for arrestation, and on Monday to discuss about function approximation. Okay, thank you very much.